the Regents Chair in Mathematics at the University of Texas in Austin. His many awards and distinctions include membership in the American Academy of Arts and Sciences, the Pontifical Academy of Sciences, the U.S. National Academy of Sciences. He has been awarded the Steele Prize of the American Mathematical Society for Lifetime Achievement, the Wolf Prize from Israel, and many others. And as of yesterday, he is the Lefschetz Medal winner of the Mathematical Congress of the Americas. Luis.
So it's a great honor to be here, and also was a great honor to receive medal yesterday. I must say, I was born in Argentina of a family of modest means, and could not have done all I did without the help both of Argentina and the United States. I mean, in Argentina, I have free education all the way, and when I went to Minnesota, I was basically received by the group there and supported for my first years a lot. So that this award is really close to my heart. Okay, so I like to sort of tell a little bit about some work that I have been doing and I keep doing that has to do with models for segregation. So models of segregation has this implication of separations, but really mathematically models for segregation appear in different contexts. One is when you have particles that, two different or several different families of particles that annihilate when they get into contact with each other, segregations of a species, also optimal partitions, that is when you have a domain and you want to split it in an optimal way to minimize values or something like that, or also when you have a harmonic maps which have a singular, whose image is a family of singular manifolds. I'll discuss that as I go along. And so I will talk about two different type of models I have been looking at. The first one is what I like to call adjacent segregation. So we have particle annihilations, and so you have these two different particles or spaces that annihilate on contact. And then I like to talk a little bit, very little, about some things we have been looking later, where segregation occurs at some distance. In other words, where I can influence things which are sort of at the neighborhood of myself, so I can keep a clean area around myself. So what I'm going to try to do is first give you an idea of how do you model segregation, how do you obtain. I'm going to talk about sort of high competition, that is where species do not annihilate completely each other, but they have a strong competition for resources. Then in the limit, you will have what it is really like clean segregation. As I said there, we are going to find what is the model for full segregation as a limit. In other words, it's much easier to model this high competition. So we are going to discuss first what is the model for high competition, and then as a limit, then we'll have a limit, and we'll have to discover the properties of the limits from the approximation problems. So basically, these are spatial models where segregations occur in space. And so, as most things, I think mathematics, there are some basic mathematical modeling tools. And in this case, the two main model tools is that, the species have some diffuse and an average around where they exist. And then there will be some terms in the system of equations that have to do with how they interact with each other. Okay. So let me first say. So I will start by saying a little bit. Everybody that knows PDEs knows that Laplacian is diffusion, and maybe a lot of people that do not know PD wonder why Laplacian is diffusion. So let me tell you why Laplacian is diffusion. So the nicest way to discuss that is in one dimension, where, in one dimension, the Laplacian is just uxx, the second derivative of x, right? And I like to think of this as a limiting of a second order incremental quotient. Okay, if you think of it as incremental quotient, then the Laplacian can be thought of this way. So you have these piles of particles, right? And they sort of, every so often, just shed particles left and right. Okay, so you have these piles. You have these piles of particles, right? And they are shedding particles right and left. And you want to sort of keep track of what happens at the point ux0. So ux0, at x0, the density is receiving particles from the two adjacent piles. So this is sort of the gain part of the Laplacian. And it is shedding itself the parts. And so if you look for the balance law, in other words, what is the net growth or decreasing at of the part x0, it is equal, of course, to of particles, which is half of the particles that come from the right and half of the particles that comes from the left, minus the particles that U is losing to the nearby piles. And this is exactly the second order incremental quotients. And when you take the limit, you get uxx. In higher dimensions, when I saw years ago, it was not, you look at the formula and you don't know why it is so special, right? The Laplacian is an equation which is invariant and independent of the system of coordinates and represents diffusion. But the issue is that the Laplacian of U can also, which is this combination of second derivatives, can really also be represented as a limit of an average. In other words, you can do the same thing you did in one dimension, right? And you say, okay, I have the particles centered at the origin, and it's surrounded by the particles that I draw in blue. And so particles are, again, jumping randomly. Make the same argument as before, ray by ray. In other words, you can say, okay, in each ray, the balance of particles is URR, right? The second derivative in that direction. So you average on the sphere, right? And if you average on the sphere, URR, take or give a constant that depends on the dimension, what you get is exactly the Laplacian. So that's why Laplacian represents diffusion. So in that sense, if you think of the heat equation, that is UT equal Laplacian U, right? The heat equation, basically what it's saying is that you have the density of U at the point X, right? And so U of X is comparing itself with its surrounding particles, because if you think on this average, right, what U is doing is U is averaging, or in the pile that I said before, U is comparing its density with the particles around, right? Makes the difference, and that's the Laplacian. So the heat equation says that U is comparing itself with this infinitesimal neighborhood, and if the average around itself is bigger than its density, then UT is positive. In other words, then U wants to increase, and if the average is smaller, U wants to decrease. So in some sense, the heat equation is an attempt by the density to revert to its surrounding average, okay? And this is, in fact, the idea that is in many diffusion processes. There's this tendency to revert to your surrounding average is what ellipticity or diffusion is about. And this can be infinitesimal, like in this, can be global. In other words, you can compare itself with a big neighborhood, and these are non-local operators then. Could be degenerate, could be anisotropic. In other words, you can weight itself more against right and left than front and back. So it's but there is always this, this reverting to the average process, which is fundamental to that provides all the averaging and smoothing properties of the Laplacian. Another issue that will be interesting or important to us in our discussion is the case in which, the particle at the center, in which there is annihilation, or there is decay, now absorption. In other words, the particle at the center, when I try to write the balance, I have the particles that come from outside, my particles that jump from my position to the outside, and that was uxx, right? But I'm also interested in the case in which, on top of all of that, I have some rate of decay or of death or absorption in my position. Okay, so when I did that balance, u of x plus y plus u of x minus y minus 2u of x, if I have a death rate, I have to add an extra minus 2 at x, which is the portion that is dying, right? And so in that case, the equation is Laplacian of u minus this portion that is dying, okay? So this will be an equation that reflects diffusion, but at some time that the particles at the position u are sort of disappearing and dying independent of the jumping at some rate, which I'll write as x squared. Maybe I should keep this in mind. Okay. So I want to point out, because I will need it later in my discussion, the properties, what is the influence of these death rates in the solutions of the equation of Laplacian, okay? So if you have an equation with death rate m squared of v, right, you can look at it in two scales. You can look at it saying, okay, my density here is 1, right? What happens far away? And so if you argue that way, you realize that to sustain, if you have a death of rate m all over space, to sustain a density 1 at this point, I have to have many, many particles outside to compensate for the death rate. And this is reflected by the fact that, that the solution of this equation is the hyperbolic cosine, right? In other words, which is 1 here, but then has to grow a lot outside to maintain my density at the origin, okay? And you can look at that way, or you can rescale do it, that is, just bring infinity to a point, and then what happens is you get the reverse effect. In other words, if you have near you sort of density 1 and you have this death rate, then your density is going to be very small at the origin, okay? And what I'm saying basically is that if you rescale this equation, right, I mean, you take this equation and instead of looking, the having density at the origin is very large at infinity, you can also express that by saying having density of order 1 nearby, then I have very, very little density left at the origin. In other words, basically, mathematically, what I'm saying is that if I take, for instance, a ball of radius h around myself, h equal to 1, let's say, and I have this death rate, and the solution around myself in the ball of radius 1 is bounded by 1, then the density at the origin is going to be exponentially small in m. In other words, as the death rate goes, the density at the origin decays exponentially in the coefficient m. Okay, and this is going to be sort of important for us later. Okay, so let me summarize, right? So suppose the consequence of what I discussed is that if you have a subharmonic function is subharmonic when the Laplacian is positive, right? If the Laplacian is positive, means that my density is smaller than my surrounding density, and therefore I cannot be a maximum because near me there is something bigger. So that means that a subharmonic function, that is with positive Laplacian, right, cannot have a maximum in the interior. The maximum is always attained at the boundary. Sort of it sinks inside, in other words. If you give me some data on the boundary, then you have a tendency to sink inside. And the other important thing then, that is that if you have a loss term of the form m squared u, then the solution u, which is bounded, let's say, around u, decays at your position exponentially fast in m. It becomes very fast. Okay. So with that at hand, then let me tell you so there are many models for, I mean, there is extensive literature for segregation, and I will comment on it a little bit later. But for, I'm going to discuss now the simplest model, right? And the simplest model is the following. You have a system of several species or particles, U1, U2, and U3, right? And then they have a system of equations, that is an equation for U1, for U2, and for U3. That is, this is the Laplacian of U1, Laplacian of U2. The Laplacian of Ui is equal to 1 over epsilon sum of Ui epsilon Uj epsilon for j different than I. Okay? And why is this a reasonable model of segregation? Because, as we said, you have the Laplacian, which is diffusion, right? So if you regroup this system like that, I have the Laplacian, which is diffusion, and then I have this term that says that the particles Ui, the family of particles of density Ui, is annihilated with this annihilation coefficient that comes from all the other particles that are competing with it. Okay, so we have that all these other particles are competing with it, so are trying to annihilate Ui, okay? And then I have this parameter, which is the high competition parameter, 1 over epsilon, right? So as epsilon becomes smaller and smaller, then the rate of annihilation of these particles against Ui becomes bigger and bigger. And so, for instance, if this sum doesn't go to 0, suppose that these sums at some point in space remains all the time equal to 1, then that means that the annihilation parameter becomes enormous. And from the decay, exponential decay I discussed before, Ui at that point is going to disappear. Okay? So this is the sort of the logic or the idea behind this system of equations for high competition. Okay? So, in fact, then what I'm going to do is I'm going to start the property of these equations. I'm going to let epsilon go to 0 and discuss the limiting configuration. Okay? And so, before discussing all the mathematical theory, let's see what do visualize, what we expect that we like to see, okay? And so let's keep in mind the following picture. The following picture will probably be the simplest non-trivial configuration, right? Will be the following, will be, suppose we have 3 different species, U1, U2, and U3 in this domain. Let's say that U1 in this region is identically 1 and the others are 0, so the particles U1 are being injected into the region. The same with the U2, here are U2 and the outside on the right, but no U1 and U3, and the same here. So U1 is coming in, U2 is coming in, U3 is coming in, and they hit each other, and then there will be this line of balance where there will be only U1s to the left, only U2s to the right, only U3 in the bottom. So this is, in some sense, the stationary picture. I mean, we have done a lot of work also on the evolution problem, but I will stay with the stationary configuration for this lecture. So the stationary picture you can hope for is that you have these particles that constantly come and annihilate itself, and then you have here a very nice curve or separation surface between U1 and U2, the same with U2 and U3 and so on, and there are some points where they come together, and so those points have some other complexity, and you would like to classify them too. Okay, so this will be the basic picture that will guide what we want to do and what we want to prove. So as I said, there is a lot of work in the literature. Let me just mention, original literature was called the Gauss-Lotka-Volterra model. Gauss was a biologist, I think. There are 2 mathematicians. So this was a competition model where there was no spatial configuration. So it was just a system of ODEs. In other words, the densities were all the same in all of space, and the species were competing, and they look who survived, who doesn't survive, and so on. Then I think
Dancer, Hillsborough, Mimur, and Pelletier, in several combinations of them, and other people did a lot of work where they introduced space consideration, rather more complex models that I'm discussing now. There was creation, there was different interactions. So it's a lot of very beautiful work by all of these people. And in fact, the model that I'm discussing now was, there was also considerable work by this group. I mean, sort of Terracini was the leader of this group, and they collaborate. They have different groups of collaboration, also provide very nice results. And most of what I discussed today was with Fanghua, and there is also some work with the three of us, with Fanghua, Karakanian, and myself. So what if you are confronted with this problem, what you would like to see? What would you like to do? Well, first you would like to show some solutions of the approximate problem, and in principle, solutions of the approximate problems are nice, since all the terms in that equations are analytic, right? It's Laplacian equal to a constant times ui, uj. So in principle, solutions are nice, but really the question is, what happens when epsilon goes to 0? That is when the diffusion starts to play, when annihilation plays a bigger and bigger role. And so if we want to study the limiting problem, the first things we need is to show that the approximate solutions converge to something. And so the best way you can do, if you don't have a fixed point theory, if you don't have something with a lot of structure, the best thing you can do is to show that approximate, you don't know uniqueness, the best thing you can do is to start by proving that the family of solutions that you have uniform continuity independent of epsilon. So that's what we want to prove, that this has uniform continuity independent of epsilon. Once you have that, you can take a limit, right? You take a limit, then we will prove that the limiting solutions are still nice. In fact, are nicer, because now there is the epsilon parameter, which was really a problem, has disappeared, and it has been replaced by a free boundary problem. So the limiting solutions are Lipschitz, and they cover all of space. There are no, although this seems obvious, right? It's not so obvious to prove it, that there are no pieces with no species, that the remaining species, the limits covers all of the domain. And once you have this configuration, then what you would like to do is to see if you can say something about the structure of the interfaces. In other words, the structure of the sets where different species come along. So what we prove here, that all of this that I'm saying is really at the end of the day is the theorems we will prove. Okay, so about the interfaces, we want to prove that the interfaces. If you look at the picture to have in mind, you have this isolated point in the middle. An isolated point in the plane has 0 Hausdorff measure, right? So what you want to prove is, in general, in Rn, that you have these interfaces which are smooth, where just 2 components come together, and then there are some singular sets where more interfaces come together, and that has to be of Hausdorff 0 n minus 2 Hausdorff dimensions. Okay, and also at those points, you see in the example I show in the picture to keep in mind. Let's see. Let me go fast. In the picture you have in mind, in fact, you can this is the plane, and so in the plane everything is nice, and you have complex variables and so on. And so here what you have is this is a harmonic function. This extends around here as harmonic functions, and this point will have homogeneity 3/2. You can do the computations just with lines, and this point has homogeneity 3/2. Okay, and so this is what we are going to prove, that we have these singular points, right, which are sort of a closed set of a small Hausdorff measure, and where asymptotically the several species coming together have some homogeneity structure with homogeneity at least 3/2. Okay? So this will be the picture to keep in mind in 3D, the picture to keep in mind in 3D or in more dimensions is precisely this. You have these three species coming together. You have, you know, that the interface between U1 and U2 or U1 and U3 is nice, and then you have this ring where three come together and have this structure. So I like to discuss in an informal way some of the ideas of some parts of the proof to give you a flavor of the mathematics that goes on. Okay? So when you're confronted with a problem like this, let me give you a senior mathematician. You first look at the 1D case because, you know, to see what happens. Okay? So in 1D case, you can only have two species, one coming from the left, one coming from the right, right? And in that case, the problem is too simple in this case because if you subtract U2 from U1, remember the right-hand side here was the same for both, right? And so if you subtract it, the right-hand side goes away. So U1 minus U2 just satisfies UXX, VXX equal to 0. So U1 minus U2 is a line, okay? So in 1D, right, you have that U1 minus U2 is a line. Now, U1 has this bigger and bigger annihilation rate, and U2 also, right, if we remember at the beginning of the discussion. So in the region where U1 is positive, in the region where the line U1 is positive, U2 is forced to go to 0, and so on. So as epsilon goes to 0, basically the limiting solution is U1 is this line, and this horizontal line, and U2 is this horizontal line, and this other line. It's two angles, okay? And then you realize that, in fact, in all dimensions, if you only have two species, happens the same. Because if you only have two species, then U1 minus U2 in every dimension is a harmonic function. So you put U1 and U2 together, and you get a harmonic function across. So in the limit, U1 will be harmonic and 0, U2 will be harmonic and 0, and this line is the level surface of a harmonic function. The level surfaces of harmonic function are as good as they get. You know, locally analytic, except for very few points where they have higher order. Okay. So what do we like to prove then when we have several species? What you want to prove when you have several species is that in the epsilon limit, most of the time there are only two species interacting. Okay? I mean, it's not plausible that you have in 3D this configuration where there are many, many places where three components come together. That would be very chaotic. So most of the time should be only two species coming together. And then what is much more delicate to prove is that the contributions, not only the other species have come together, but the right-hand side contributions of the other species came out, because that was going to infinity, and all of a sudden you say it's 0. So this is a much more delicate thing. So, but you want to prove that, and you want to quantify most of the time. And most of the time will be that is except the singular set of Hausdorff dimension n minus 2. Okay, so basically this is what you expect to be the theorem, is that most of the time, the level surfaces that I said we should be smooth are actually harmonic functions, and there are this set of singular points which are where several pieces comes together, but in that case, the solutions are homogeneous. Okay? So let me discuss a little bit the parts of the proof and focus in the ones I like the best. So the construction of a family of approximate solutions is just a fixed point theorem, and it's not hard to build. And then the issue is that they are uniformly held or continuous, and this is not trivial, but it is reasonable to do. In fact, it's based, in some sense, in some work I did before with Roque Joffre for flame propagation problems that have a similar structure. So you have to look at the system and see, well, one of the components have to decrease and so on. It's not such a, I mean, it's okay. So what really I like to go now is to the, what really I like to go now is to the fact that, to give you an idea of how can you prove that the limiting solutions are just a bunch of disjoint harmonic functions, and they are all of a sudden Lipschitz continuous. Lipschitz continuous, this bounded gradient, in some sense has jumped above the regularity of the approximating solution. It's much more regular, and in fact it's the optimal regularity, because you expect U1 to be a nice density that becomes 0, and then it's extended by 0, okay? So Lipschitz regularity is already a jump on the expectations, the obvious expectations of the problem. And so I really like to give you an idea of how do you prove this, because it involves some nice ingredients, okay? So you have to prove everything through the epsilon problem, because all you know about the limit is that it is the limit. At this point, you don't know equations, you don't know anything. So you have to do all the computations through the approximating problem, and then see that they carry to the limit. Okay, so, but this, I chose this, then I'll discuss, you know, the work we want to find why involves some much more delicate things. But this is nice because it has a lot of very nice cancellations. Okay, so the first cancellation you notice is, you know, before we have that U1 minus U2, when you only have two species, we have that U1 minus U2 was harmonic. That is gone now, right? Now, but you realize that if you take U1 minus the sum of all the others, then the positive terms in U1, which are U1 UI, reappear negative on the others as minus UI U1. The common terms all reappear. So that means that all the positive terms that come from U1 have disappeared, and therefore U1 minus the sum of the rest is a superharmonic function. In other words, the Laplacian is negative. Okay? So instead of the annihilation issue, now we have negative Laplacian. Okay? And the other observation I want to make is that if you have any finite group of them, which I take U1 plus U2 plus U3, right, or something like that, that combination still is subharmonic, because the right-hand side of each one of them was positive, right? And so when we add them up, we have something positive, okay? So we have to play these two properties. One is the superharmonicity of this term, and the other is the subharmonicity of this term. And superharmonicity and subharmonicity always go through to limits, because they are really distributional concepts. You know, it is, in other words, if you have a sequence of functions which are in bounded or in L1 or whatever, and they are superharmonic, the limit is also superharmonic, because it's a thing in the sense of distribution. So, you know, if the functions converge, the distributions in some sense, the derivatives in this sense of distributions converge. So here, when epsilon goes to 0, we know automatically that the limit is still, of these combinations, is still super or subharmonic. So I'm going to use when I discuss the proofs, I'm going to use two monotonicity formulas. And monotonicity formulas have this magic appearance more and more in geometry, in PDE, and so on. And so I'm going to take some time to try to explain you what does a monotonicity formula mean. Even if I don't get to the end, I think this is something that is interesting. So monotonicity formulas usually say that you take a solution of a PDE that can be a minimal surface, or can be a harmonic function, or some nonlinear equation, right? And monotonicity formula says that there is a quantity, so you start at the origin, right? And you start to go away from the origin. Suppose you have a harmonic function, right? You start at the origin and you start to go away from the origin, and so there is some quantity that has some role of entropy that grows as the radius increases. Okay? And there are some very classical monotonicity formulas. One, for instance, is, and is very powerful for minimal surfaces, right? That says that if you have a minimal surface in Rn, and you look at the area of the minimal surface inside the ball of radius r, right? So you take the area of the minimal surface inside the ball of radius r, more or less should be like r to the n minus 1, because it's area, right? So if you take a plane, the area inside this ball of radius r is exactly a constant r to the n minus 1. And so the area formula says that if you take the area and you divide it by r to the n minus 1, that increases by r. So this is a classical monotonicity formula for minimal surfaces. It's very important because it gives most of the regularity. Another is that if you have a harmonic functions and you take the gradient of the harmonic function square and you average on the ball of radius r, also that increases with r. In fact, these two quantities remain constant only if the surface is a cone. In the case of the minimal surface, this ratio remains constant only if the minimal surface is a minimal cone, and in the second case, only if the harmonic function is a plane. Okay, so I'm going to use two monotonicity formulas. One that I developed with Alt and Friedman many years ago, and another one, which is very well known, is the Almarin frequency formula to describe the geometric structure of the interface. So the first one is for Lipschitz. The second one is to describe this structure, homogeneous structure of the singular points that I talked about before. So the formula we proved with Alt and Abner-Friedman says the following. So let me show you the picture first. Suppose you have a domain, right? And you have two subharmonic functions that are joint support, right? So they have the blue and the red, right? They are non-negative and subharmonic, which is something we have, right? Because the sum of the USJs have that property. And they have this joint support, and they both vanish at the origin, okay? And then you look at this, you start from the origin, and you look at this quantity that expands away from the origin. In other words, you look at, this formula looks a little bit strange, strange, but really is the gradient of V square over the fundamental solution of the Laplacian normalized, okay? So you look at this product that says how both functions, this term is increasing, okay? And so the monotonicity formula says that this quantity is increasing in R, okay? Now, this quantity, when R is equal to 1, is bounded by integration by parts. You can see that it's bounded. So that means that since it's bounded when R is equal to 1 and it is increasing, it's bounded for any smaller R, okay? But this quantity is sort of an average of gradient V square. In what sense? Well, the ball of radius R, right, has volume R to the n. So if you want to average, you have to divide by R to the n. I'm not dividing by R to the n here, but I have the R square and the little r to the n minus 2. So let's say that philosophically or morally, this quantity is, in some sense, when you integrate, of the same order as this. If you think that these two quantities are of the same order, then this formula says that the product of the averages of gradient square are monotone, okay? In fact, this quantity is constant only if V1 and V2 are planes. Okay, so this quantity is constant only if V1 and V2 are planes, and in fact, when R goes to, if you let R goes to 0 and V1 and V2 are nice functions, then you can prove that this quantity converges to the product of the two normal derivatives. Okay, so this is something very delicate, for the people that does harmonic analysis. This, in some sense, says that the harmonic measure at both sides of the domain have this property that the product is bounded. So if harmonic measure gets to be too big on one side of the domain, it has to be very small on the other. Okay. So this is what we will take of this this monotonicity formula, the control of the product of the normal derivative, right? And so, as I said, a typical configuration will be this one. And now let me apply this monotonicity formula and this typical configuration to our problem. Okay? So I can apply this configuration to U1 and all the rest, right? Because U1 was subharmonic, and all the rest, the sum of all the rest is subharmonic too, and they are disjoint. So I can apply this theorem to U1 and all the rest. Okay? So if I apply this theorem to U1 and all the rest, I mean, this is all in a very generalized sense, because, to make sense of all of this takes a lot of work. But let's assume that we can do that, right? Then what I get is that the product of the normal derivative of U1 times the normal derivative of all the rest is bounded, okay? But, you see, also we know that U1 minus all the rest, that is, if I take U1 and I flip it and make it negative, that combination is superharmonic. Okay? Now, suppose that they look as a plane at that point, right? So you have the plane of U1, I have the plane of all the rest, right? The product of the gradients, that is of the normal derivatives, is bounded, but since the combination is superharmonic, it cannot have a positive angle. If you have a positive angle, the second derivative where planes get together is a positive delta. So if you know that the combination is superharmonic, the angle has to be negative at best. I mean, it can be smooth or negative. So what this is telling in our case? In our case, this is telling us that the slope of all the rest, right, beats the slope of U1. So we have that U1 times all the rest is bounded, and all the rest is bigger than U1, therefore the normal derivative of U1, therefore the normal derivative of U1 is bounded. And so once you know that all along the interface the normal derivative of U1 is bounded, then you can pass to the interior. It's a standard technique for harmonic functions. So this is the way that you get that the limiting solutions are Lipschitz. About the Ambry monotonicity formula, I just like to discuss a little bit the structure of the formula. I will just mention how do you apply it, okay? So Ambry monotonicity formula says the following. It says you give me a harmonic function, okay? You can make it 0 at the origin. Make it 0 at the origin. And then what you look is at the integral, the solid integral of gradient u squared times the surface integral of u squared normalized by r. And this quantity is increasing in r. Okay? And you can prove it just by using spherical harmonics, or by taking the derivative of the equation. I want to make you notice, because although this is not pertinent to the lecture, comes to this idea that monotonicity formulas are a measure of growing entropy, right? I want to point out to you that really the terms, this volume term for a harmonic function is really a boundary term. Gradient of u use integration by parts, and gradient u squared is u nu. This term is really the h1/2 norm of u on the boundary of Br. So really, the Ambry monotonicity formula is a Rayleigh quotient. It's a Rayleigh quotient in the sphere of radius r of the h1/2 norm of u over the L2 norm of u, and normalized by the correct factor r, because h1/2, right, is half a derivative. So when you take the square, it's r. So Ambry's monotonicity formula basically says that if you take a harmonic function and you look at the normalized Rayleigh quotient in the sphere of radius r, that grows with r. And the growth of a Rayleigh quotient is really a measure of disorder, right? In other words, the minimum of the Rayleigh quotient gives you the first eigenvalue, and as the Rayleigh quotient grows, it gives you more and more complex eigenvalues. Okay. What is good about this formula? See, you can always renormalize this formula. In other words, you can take the point and start to expand and expand. And if you expand the solution, that is equivalent to looking at the formula closer and closer to the origin. But this is a monotone function, so it has a limit at the origin. So if you look at h closer and closer at the origin, at the end of the day, when you have blown up everything to infinity, H is constant. And Almgreen's monotonicity formula says that if H is constant, then U has to be a harmonic polynomial. Okay? So in some sense, Almgreen's monotonicity formula, when you apply to the level surface of a harmonic function, really stratifies the harmonic function, because it can only be, since when H is constant, can only be the degree of a polynomial, means that H can only be or 0, or 1, or 2, or 3, or so on. Okay? 1 if the function starts like a polynomial of the degree 1, a plane, and 2, a quadratic polynomial, and so on. So Almgreen's monotonicity formula says that, you have on the 0 level surface, you have H of 0 equal to 1 most of the time, which is when the gradient does not vanish, and then you have quadratic polynomials and so on. And so the way we apply it in our case is just, we just realized that we more or less could redo this formula for our problem. And so when you redo this formula for our problem, you have again the H of zeros for every point in the free boundary. Okay, and then they stratify here in a different way, because it's not like the polynomials. It's not that H can be 1 or 2 or 3. H can be 1 or 3/2, like in the picture that we have to keep in mind, or 2 or 5/2, and so on. It jumps from half to half. Okay? So, but what is important is that we have this gap. We have this gap that says that H of 0 is or 1 or 3/2, or bigger than 3/2. And so the sets where it's 1 are the sets where only 2 components comes together. And then what we have to prove is that the sets where it is bigger than 1 has jumped to 3/2 is where at least 3 components come together. And this is basically what we do. Okay, now this is not the end of the day, because you can have, Almgreen monotonicity formula tells you that the configuration at the end is 2 planes, but but these 2 planes can have other skinny components coming by. It's not, and so to get rid of this, we have to do some sort of cleanup lemma, which is a recurrence argument in the de Giorgi's in some sense that says, when these other components are very skinny, they are squeezed so fast that at the end of the day, they never reach the origin. Okay, so that's the way you prove that where 2 components come together is completely clear. There are, this was the simplest model, but there are many other interesting models. And many of them, you don't have these nice things that when 2 components come together, it's a harmonic function. 2 components come together, you really have a jump condition, and it's a free boundary problem, and you really have to prove that these regions are really smooth surfaces. So some examples are, one is, for instance, variational problem. See, like if you do this variational problem, right, you again have high annihilation, but have a subtle change, which is that this is uj squared. And this isn't like a minimal change, but has the effect that all the tricks of the difference being super harmonic, the right-hand size cancel, and so on, disappears. So you have to develop other methods. Optimal partition is you take a domain and you say I want to split in a family of domains such that I minimize the sum of the eigenvalues of the Laplacian, right? And it's mathematically very close, but has another type of difficulties. Another problem we treated has to do when there is not just everybody against each other, but there is groups, group 1, U2, U3, against U4 and U5, and against U6, U7, and U8. And in that case, then you have a combination like the old ones, but where they are not so nicely mixed. And there you really get a full free boundary problem. The interaction between the 2 sides is much more complex, and we have to do other things. Okay, so now in what is left, let me say just a few words about this thing we have been looking at, segregation as a distance. So basically the equations are very similar to the previous ones. In other words, you have that each one of the U1s has diffusion and then has this annihilation rate. But the annihilation rate now, the annihilation coefficient that before was a combination of the other functions at that point, really is now a non-local term. In other words, now u2 not only at the point x, but nearby is able to try to annihilate u1 of x. So, you know, for instance, a typical example is if you have, you know, if the UKs sort of are able to produce a chemical inhibitor around them, right, then the competition, it doesn't happen, you know, at contact, it happens wherever the inhibitor reaches. And in problems of finance, too, there are a bunch of areas where these type of things appear. Okay, so let me just, let me say, okay, what is this annihilation term now? This annihilation term at the point x, as I said, not only involves u2 at x, but involves u2 at nearby points. In other words, here I have the point x, and the values of u2 anywhere at any of those points can reach me, right, are affecting me. In other words, I'm now sitting at the center of this ball, and they are sort of attacking me from everywhere where I at distance bigger than 1. So typical term could be or the supremum, that is just is enough that somebody is big here to annihilate me, or some integral that is, they need an average to annihilate me, and I put here u1 or u2, okay? So for me to stay positive somewhere, then it is enough that if the annihilator stays positive somewhere at distance 1 from me, then this quantity will go to infinity where I'm standing, and I will be annihilated, okay? So basically, what do we expect? Then what we expect is that the species be at distance at least 1, right? In other words, if this is the ball of radius 1, the species be at distance at least 1, okay? Whoops. Yeah, okay. Let me, all my discussion here have been sort of, this is related more like to probabilistic reasons, has been non-divergent, but they are very nice divergence problems. And one that I didn't, no, what I say today applies in some sense, but would be very nice to have a more deep variational understanding, I think, is this one, right? You have the two species gradient u1 squared, so you have that you minimize the diffusion part, and then you minimize a double integral of u1 at x and u2 at y for x minus y at distance less than 1. And this is exactly one of the examples before, because the Euler-Lagrange equation that you get is that the Laplacian of u1 is equal to u1 times the integral in the ball of radius u1 of u2. So this is exactly one of the previous examples, but it has a variational underpinning that may make it very interesting. Okay, so what is the picture we have in mind here? The picture we have to have in mind here, I mean, our goal is the following, so a nice configuration to discuss our goal will be the following. So we have this strip, right? We are on the bottom of the strip, u1 is only u1 and no u2, and the top is only u2 and not u1. And then what you expect is that here will be the support of u2, where u2 is harmonic. Here the support of u1, where u1 is harmonic. And in between there will be a nowhere land, right? It's like I don't know, the trenches in the first war, World War, right? Where there is this nowhere land, right? And what you would like to prove is that this nowhere land has some structure. And the structure of this nowhere land is that the boundary of u2 is exactly the points which are at distance 1 to the boundary of u1 and vice versa. So I'm making this picture, this angle, right? And if you take the distance function to this angle, then it is like a piece of a circle in 2D, right? So this is what you would like to see. Yeah, I still have at least 7 or 8 minutes, right? Because I remember at 30, people was very slowly coming in. Okay, so this is the picture we would like to see, right? And so the main theorems is that you have the approximating solutions exist, The limiting solutions, again, you have to prove that they are Lipschitz and harmonics in their supports, right? And as I said, that they have these optimal configurations where each one is exactly the level surface to the distance function to the other one. Okay, so this is an important geometric factor, because one thing it says is that the U1 has the boundary of U1 has always by outside a tangent ball of radius 1. So for instance, these the surfaces are always surface of bounded below curvature, and gives a lot of geometry. Okay, and in 2 dimensions we can prove in the nice configuration that I gave before that they are actually C1 surfaces. And in more dimensions, we don't know, because it needs a delicate geometric argument. And so I just make a comment on the proof. So let me go back to the very beginning, where I said that if U is a non-negative solution of this equation, then you zero the case exponentially fast on M. Okay, and so we have now is where we really use that property, because we want to prove that if U1, let's say, remains non-trivial at the origin of the ball, that means that U2 is completely wiped out, not only of the ball, but from even a little larger neighborhood of the ball. Okay, and so in principle, why is that? So in principle, to apply that, we really don't need a point. We need more than a point. We need a little neighborhood of the point to have some mass, because in many of my examples, I'm integrating. So to have some mass, I need to know that there is a little bit more of mass around that point. Okay, and this is attained just by a barrier argument. In other words, here is my candidate to annihilation and the ball of radius 1, and I want to show that my poor candidate to annihilation, the ball of radius 1, still has some mass of the lambda at the origin. And for that, you just made a barrier argument and show that the mass at lambda has to propagate a little bit. Okay, the proof that they are exactly at distance 1 is very delicate, because it really has to relate the right-hand sides, and the right-hand sides between 2 points at distance 1, and it's not obvious how to relate it, because one involves U1 here and an average in the other, all the ball, and the other involves U2 there and an average on its ball. So it's not clear how you relate it, but we manage for smooth convex sets, for a smooth convex set. In fact, the final comment is that basically you can do this for general sets, except for the last part, can be any star-like set, right? It's important, when you look at the proofs, it's important that the sort of the area of influence of each one of the species has to be in some sense conjugate to the other one. For instance, if the 2 species will have the same area, this same area of influence, then the one on the right will just wipe out the one on the left. The one on the left has no defense towards the large reach of the one on the right, right? So it is exactly this symmetry between regions of influence what produces a balance, between the 2 annihilations. And so in that sense, I think there are very nice problems to look at. For instance, I think if the weights and the shapes are different, on what conditions they are equilibrium points. Suppose that one has a region on an ellipsoid and the other on a sphere, right? If the sphere is much larger than the ellipsoid, clearly the sphere is going to wipe out the ellipsoid. And the other way around too. But then there must be the question, is there some point, if you give me 2 different sort of annihilation formulas or ways, is when is there what are the cases when there is some balance that will give a stationary configuration? If you look at an evolution problem, right, and let's say that the ball of the area of interaction of U1 is a little bit bigger than the area of interaction of U2, is that going to wipe out the thing instantaneously, or is going to be sort of a traveling wave solution? Maybe they are trivial things, but we have not looked at it, and I think there are some interactions, and also the higher dimensional smooth is geometrically rather hard, it's harder, and that's it. Thank you very much for your attention.
I think since the audience is very large and we now have a coffee break, I suggest that people come and personally ask Luis comments, and I'm sure he'll be very happy to talk to you. Thank you again.